In this video, we are going to look at how you graph the reciprocal of a function, in particular, a linear function. So here's the function that we're going to graph, f at x equals 1 over 2x minus 4, which is the reciprocal of the linear function p of x equals 2x minus 4. So this is would be our linear function, and the reciprocal of that is 1 over 2x minus 4. When you graph a reciprocal function, there's 5 things you're going to look for in order to graph it effectively. Those are these 5 things. So we'll go through those steps and see how that helps us produce the graph. So the first thing we look for is the y-intercept. So the y-intercept, hopefully we know, that's f of 0. So we're just going to sub 0 into our function 1 over 2 was x, so it would be 0 minus 4. So this is going to be equal to negative 1 over 4. So therefore, the y-intercept is 0, negative 1 over 4. Now, one thing sometimes people will ask, what about the x-intercept? Why aren't we looking for the x-intercept? And the reason you can't find an x-intercept is, or you don't look for the x-intercept, is because there isn't one. Remember that the function is f at x equals 1 over 2x minus 4. Well, we want to figure, if there was an x-intercept, we would set this equal to 0, and we'd want to figure out where does this fraction 1 over 2x minus 4 equal 0, and the answer is never. 1 over something can never be equal to 0. So that's why there's no x-intercepts for any reciprocal function. We'll never have an x-intercept. But what we do want to find is the vertical asymptote. Now the vertical asymptote, we should know that that will happen wherever this function is undefined. So all we need to do is take the denominator, in this case that linear function, 2x minus 4, and set it equal to 0. We get 2x equals 4, so x equals 2. So therefore, there is a vertical asymptote of x equal 2. Okay, going back, the next thing we want is points where y equals plus or minus 1. This one I just want to talk about for a second as to why we're doing this. So points where y equals plus or minus 1. Remember we said we can't find, just mentioned, we can't find the x-intercepts. That's because this function f at x will never be equal to 0, right? To get an x-intercept, you let y equal 0. And the reason that you want, like, you ask yourself, why do you usually get x-intercepts for a graph? And the reason is it's a point on the graph, and the more points you get, the easier it is to graph. The problem with this one is you can't get the x-intercepts. So what you say to yourself is, can I get another point? And thinking back to the x-intercepts, why is it the x-intercepts the thing that we usually find? Why do we usually set this equal to 0? And the only reason is that's the easiest thing to set it equal to, right? It's easy to set this equal to 0. That gives us the simplest equation to solve. But we know for this one that's not going to work, so we pick the next easiest number. What would the next easiest thing to let y be equal to other than 0 be? And the answer is 1. So if we take this equation, set it equal to 1, and then solve. So the way you would solve this, remember that this is a reciprocal 1 over 1. So if you just took the reciprocal of both sides, you'd have 1 equals 2x minus 4. And now you're just solving a simple linear equation. So that would be 1 plus 4 equals 2x. 5 equals 2x. So x is equal to 5 over 2. So therefore we have a point. The point is 1, 5 over 2, right? Oh, sorry, I got that backwards. The point would be x is 5 over 2, y is 1. So we can put that point on the graph. And then we can do the same thing if we let y equal negative 1. So negative 1 equals 1 over 2x minus 4. Solve it in the same way. Take the reciprocal of both sides. So we have negative 1 equals 2x minus 4. So minus 1 plus 4 equals 2x. So we have 3 equals 2x. So x is equal to 3 over 2. And that gives us the point 3 over 2 minus 1. So that just gives us 2 points on the graph to go along with the y-intercept that we already found. That would just help us graph this function. The fourth thing is end behavior. So another question sometimes people will ask is, if we found the vertical asymptotes, why aren't we finding the horizontal asymptotes? And we actually are. End behavior really is just a description of just if there is horizontal asymptotes, that will come out from your end behavior. So remember, that was our original function. And in order to get end behavior, we say as x goes to infinity, what's happening to y? So this will just take a little bit of thought here as to what's happening. Let's think about that polynomial, which is this, what the original function was. P at x was 2x minus 4. So remember, 2x minus 4. What would happen to this function as x goes to infinity? And hopefully we know that p at x would go to infinity. Now what does that mean? That means the y value here is getting very, very large, right? So large positive numbers, so like 1,000, 1,000,000, 1,000,000,000. So if you take the reciprocal of a very large number, right, if you have 1 over something which is approaching infinity, so 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000, what is that approaching? And the answer is 0, right? 1 over 1,000, 0.0001. 1 over 1,000,000, 0.000, a bunch of zeros, 1. So very, very small numbers. So what is y approaching? 0. If you go as x goes to minus infinity, y is approaching, again, what would be happening to this? P at x would be approaching negative infinity in this case, if you put in a very large negative number. So 1 over a very large negative number, 1 over negative 1,000, 1 over negative 1,000,000, is a very small number. So that this would also be approaching 0, which means, and we've talked about that as end behavior before, that means there's a horizontal asymptote of y equals 0. Okay. So we have a horizontal asymptote of y equals 0. And then the last thing was positive negative intervals. And we did this with polynomials. Now some people, or some of us, would have not done this. So I think I had said you don't need positive negative intervals to do polynomials, but you do for reciprocal functions and rational functions, which we're going to do next. So the way you figure out the positive negative intervals is you set it up in a table. So here I'm just going to look at my function f of x. And here I'm going to take my real number line minus infinity to infinity, and I'm going to break it into two intervals. Now, when we looked at polynomials, the intervals were separated by the x-intercepts. And now, for this function, there is no x-intercepts, but there is still a point, an x value, that you have to separate the intervals into, and that's where the vertical asymptotes occur, because the function could change from positive to negative at those values. So the vertical asymptote in this case occurred at 2. So now what you're going to do is take a value between negative infinity and 2. So 0 would be an example of a number in that interval. Substitute it into f at x and just determine, do you get a positive or a negative number? And you get a negative number. If you substitute in a number bigger than 2, so like 10, you get a positive number. So therefore, f at x is less than 0 if x is in the interval from minus infinity to 2, and f at x is bigger than 0 if x is in the interval from 2 to infinity. Okay, so now we're going to take all that, put it together to graph our function. So draw your axes, set up a scale. So you want to make sure that scale allows you to include all key points and vertical asymptotes. So there was a vertical asymptote at 2. Label the vertical asymptote. So this would be x equals 2. Label your scale as well. Put a y scale on there, so that'll be 1. So put on your asymptote. So x equals 2 is 1. Y equals 0 was the other one, which is the x-axis, so I don't need to put that point on. You need to put on all key points. So going back, our y-intercept was 0 minus 1 over 4. So we'll put that on our graph. 0 minus 1 over 4, so minus 1's down here, minus 1 over 4, be around there. We had those 2 points here, 5 over 2, 1. So if you need to convert to a decimal to help you graph, that would be 2.51, and this would be 1.5, negative 1. So put those 2 points on. So 2.51. So 2.5, say that's 3. So 2.51 would be right there. And 1.5, negative 1 would be right around there. So we have 3 key points, a y-intercept, and then the points where y equals 1 and negative 1. I could label those two. So this was 2.51, and this was the point 1.5, negative 1. And now I'm just going to connect these points, making sure I'm approaching the asymptotes in the correct way, and using the positive negative intervals to make sure I'm on the right side of x. So remember, the positive and negative intervals told me that f at x was less than 0, so that means below the x-axis down here if x was in this interval. So I'm going to connect these points. I have to approach this vertical asymptote. Got to be going down. And then I'm going to approach this horizontal asymptote of y equals 1. Okay, I'm never going to cross the x-axis because 1, it's a horizontal asymptote, and 2, I know that f at x is always less than 0. Now for this side, I know that f at x was positive for values bigger than 2, so it's always going to be above the x-axis. It's going to approach the vertical asymptote, so it must go up towards the vertical asymptote, and then here I'm going to come down and approach the horizontal asymptote in this way. So that would be your reciprocal function, f at x equals 1 over 2x minus 4.